This lesson is about transforming graphs. So we're going to look at all the different ways we can transform graphs around. First, we just want to have a look down at all of these highlighted functions and think about if we graph these, what would they all have in common? You might think, I don't have time to graph that. I'm very busy, so I've done that for you. Let's just click all of these on and off and see what happens. Oh yeah, it looks like a curve. Oh yeah, curve. Oh yeah, curve. Oh, upside down curve. Oh yeah, shifted to the left curve. Shifted to the right curve. Shifted to the right and a bit skinnier than the others. That's a really skinny sort of curve. That's an exceptionally skinny curve. So I can turn all these on. Hopefully by looking at all these graphs, you can see that the thing that they have in common is that they have that parabola shape. Okay, so they're all parabolas. Okay, and they're all essentially y equals x squared shifted or dilated. Okay, dilated is a fancy name for stretched or squashed together. Alright, but we'll always use the word dilated. Where have you heard the word before? If pupils are dilated, pupils have gotten bigger, they've expanded. So we want to have a look at how we can draw all of these different graphs from our, I guess, base function, the x squared one. So we want to have a look at what multiplying functions by numbers does. Okay, so we want to investigate these transformations in a pretty systematic way. So we're going to start with some function, just the x squared function, and see what happens if we multiply the function by a. So if I multiply left hand side by a, I'll multiply the right hand side by a as well. So I'm looking at what does ax squared look like. So the way I'm going to do this is I'm going to complete the table of the values of f of x if my function is just x squared, and then I'll look at what 3 f of x looks like and what 0.5 of f of x looks like. So I'm just going to use my calculator and find what f of minus 4 is. So I'll put minus 4 squared into my calculator, I'll get 16. And I'll do the same thing for the rest of these. And then I'll think, well, what happens if there's a 3 in front? So I'm trying to find 3f of x, so I'm substituting minus 4 into here. So 3 times minus 4 squared, give me 3 times 16, or 48. Okay, and I can do the same for all of these points. Yeah, and I'll do the same for the half as well. So I'll put minus 4 in here, 0.5 minus 4 squared. Okay, I get 8 for this first one, and do the same all the way down. From here, I'm going to graph the 3 functions on the same set of axes and see what happens when I multiply the function by a number, like multiply it by 3 in the red case or by 0.5 in the black case. So I'll just go ahead and mark all of my points and see what it looks like. So that's what my base function looks like. It's a parabola. Looks a little bit stretched out, but that's just because of the way I've drawn my axes. Now let's have a look what happens to the red one when I've multiplied everything by 3. So that's what 3x squared looks like. So what we've done is this distance here has been stretched. So it's been dilated or expanded by 3 times in a vertical direction. That's why it's called vertical dilation. So let's now have a look at what happens if we multiply by, say, 0.5. So having a look at the green function, we can see what's happened here, that the vertical distance has been halved. Okay, it's been dilated by a factor of 0.5 or halved. And so that's what we can see with what's happened. So what's the effect of a on the normal function? We can write something like this, that the function is vertically dilated and it's stretched if a is greater than 1 and compressed if a is less than 1. So compressed is probably a better word than squished down. So we'll turn the page and have a look at what some horizontal dilation looks like. So what we're doing is putting bx inside the function instead of x. So the way this will appear will be, the functions will look like this, bx all squared. So again, we'll complete these tables. I'll just do the first one of each as a demo. For the functions x squared, I'm looking for f of minus 4, which would be minus 4 squared. I'll put 16 in there. If it's 2x squared, okay, I'll be looking at putting minus 2 inside these brackets. So 2 times minus 2 squared, minus 4 squared, gives me 16. And a similar thing down here, 0.5 times minus 8 squared, give me 4 squared, give me 16. So you can go ahead and complete the rest of that table, substituting in values, don't cheat. Once I've completed the table, I'll graph all three relationships on the same set of axes, again in those three different colors. So this is what my base function looks like, the x squared function. Again, it's parabola. It looks slightly different to the one on the previous page, but that's just because my axes are slightly different again. Let's now draw the red graph, so 2x in bracket squared. So a little bit harder to see what's going on, but we can see that in the horizontal direction, the distance from the x-axis to the curve has essentially been halved. Okay. Another way we can think about this is both of the functions are eventually going to get to 16. Imagine the 16 point here is their goal. My red function, the 2x squared function, gets there faster. Okay, it gets there in less time, only takes 2 units instead of 4 units, because that b value, that 2 value, is making things happen earlier than they would for the x squared. So let's draw the green one and see how that compares. Look at my green graph, I multiplied it by half. What's happened? The horizontal distance to the normal, or the base function, has now been doubled. Okay, again, thinking of it in terms of reaching that goal. If this is my goal, I've reached it a lot later. Okay, imagining that the horizontal distance is time. So I'll have a look at what's happened. What's the effect of b on the function? Well, there's been a horizontal dilation. Okay, we're stretching, getting further from the y-axis horizontally if b is less than 1, and compressing, getting closer to the y-axis if b is greater than 1. So I'll turn the page and have a look at some translations. So I've looked at the 2 dilations, the 2 stretching. Now we'll look at translation, which is a fancy way of saying shifting. Okay, so we'll do the same thing. We'll look at these 3 functions. What we're doing is we're adding something onto the function. So whatever my function was, x squared, I'm going to add some constant k to it at the end. Again, I'll just do the first 3 as a demo. So this first one would be minus 4 squared, 16. And next one, minus 4 squared plus 2, which would be 16 plus 2, give me 18. And this last one would be minus 4 squared minus 1, 16 minus 1, or 15. I can go through and fill out the rest of the table. So from here, go ahead and graph the 3 graphs, seeing what the effect of adding 2 or subtracting 1 has on that original function. There's the original graph. There's a graph when you add 2. So let's have a look what happens. For the red function, when I added 2, everything shifted up 2. For the green function, when we subtracted 1, everything went down 1. So what's the effect of k on this function? Well, the curves shifted vertically in the direction up if k is positive, and down is if k is less than 0, if it's negative. Okay, one more translation to go. we're looking at horizontal translation. Okay, so where we've got f of x plus h, probably brings back nightmares for some people. Okay, so I'm looking at what's x plus h squared look like. So again, looking at these three curves. Okay, first point here, minus 4 squared, 16. It's always 16. And here, I'm after minus 6 plus 2 squared. So I'm really ending up with minus 4 squared. Okay, so I get 16 here. So at minus 6, I get the value I would have got at minus 4 in the original function. And this last one, minus 3 minus 1 squared, so minus 4 squared again, give me 16. So here at minus 3, I'm getting what I would have got at minus 4. So we'll plot the rest of the points and graph them and see what this horizontal translation or shifting is all about. So I completed these and I've sketched the red one. Hopefully what you can see from the red graph is when we added 2 inside the function, okay, the function is squaring, we added 2 inside it. What's happened is that it's all shifted 2 units to the left, which is sort of the opposite of what you'd expect. So I'll have a look at what happens for when we subtract 1 inside there. Then we have a look at this green one when we subtract 1 inside the squaring function. What it's done is moved to the right. Okay, so what's the effect of h on the function? Okay, the h value horizontally translates the curve. So to the left when h is positive, like for example this red curve, we went to the left, and to the right when h is negative, like this one. Okay, so over the page, so there's a summary of the 4 translations that are possible. Okay, and it really depends on what my function is. If I have all of these letters and my function originally was x cubed, then all of these combined will look like, I'm going to multiply the thing by, so I'll start from inside. I'll add h, and then I'll multiply by b, and then I'll apply the function. So I'll cube everything, and then I'll multiply by a, and to the final result, I'll add k. That's as hard as it's going to get. Okay, there are just 2 special cases with these dilations and translations, which are some reflections. So we'll just have a look at what these look like. So we'll just complete a table, see what it looks like, and draw the 2 graphs. Okay, so in here we're just squaring, so minus 3 squared. Look at f of x equals x squared compared to minus 2x squared. So in here will be minus 2 times minus 3 squared, which will be minus 2 times 9, or minus 18. So we'll complete these tables and graph it, see what it looks like. Should be minus 18. So what you can see is if the a value that we're multiplying by is negative, it'll reflect in the x-axis. So imagine this x-axis is a mirror. The original graph will flip over into that axis. So we'll just note that there so we remember what negative a values do. And we'll have a look at what a negative b value would do as well. So have a go at completing that table. Okay, just note that we're graphing an x cubed function. So when we're substituting in these values, we need to be careful about cubing. So minus 2 cubed will be minus 8. Whereas over here, minus 2 times minus 2 cubed will be 4 cubed. Okay, or give us 64 or whatever it is. Okay, so go ahead and complete it, see what it looks like. So in this final one, a negative b value, it's a little bit hard to see. If I extend this black line out a bit more, it should be easier to see. What's happened here is that it's reflected in the vertical axis. So it's sort of reflected in that way. Okay, so for negative b values, it'll reflect or flip over the y-axis. Okay, so in addition to these four ideas of what A, B, H, and K do, we also have these reflections. So now let's actually use the things. Okay, so I want to draw what these things look like. I'm given what the function looks like. I'm not told the equation of it. I'm just told that we're going to do these transformations to it. So in the first case, I'm multiplying the function by 3. So this is indicating that my A value is 3. Look back on my grid. A values are vertical dilations. So that means I should be stretching things vertically, or making the distance from the horizontal axis bigger. So all these distances here I'm going to make bigger. Okay, so I see that it's stretched out. This distance here needs to be bigger, so I'll stretch out to here. Since this one's on the axis, we'll still go through the axis, and then in the negative direction we can stretch it out as well. So if I want to draw what 3f of x looks like, I can scribble it on the graph and then draw what the new one looks like. What about if the 2 is inside? That looks like a b value to me. It looks like it's a positive b value, which means I'm going to compress it horizontally, so make it get closer to the y-axis. So all these points need to get closer to the y-axis. So on the left of the y-axis they look the same, but these other ones, they're going to all halve in distance. So it looks something like this, in that the vertical distances haven't changed, we've just shifted it in horizontally. So should look something like that on my graph. Okay, 2 more to demonstrate the full range of these transformations. So I'm adding inside, so it's going to be a h value. H equals positive 3. Okay, positive 3 tells me that it moves 3 units to the left. So over at 3, I can shift all this stuff over. It's all going to happen exactly the same, but pass through this point at 3. So exactly the same shape, exactly the same height, just all shifted over, and I can draw that on a fresh graph if I want to. Okay, final one, we're adding after the function is complete, so that's a k value of 2. Positive k value means shift everything up, so I'm going to move all these points up 2 units. Okay, everything shifted up 2 units. That sort of look like the same shape, just shifted up, and we can draw that on a fresh graph as well if we want. Okay, so that's what these transformations will look like individually. If I was going to do a whole heap of these in the one transformation, looks a bit intimidating. I should have another bracket here. Okay, so this is my a value equals 3, which is telling me to vertically dilate. And I need to state that. This 2 is a b value, okay, also telling me to vertically dilate. Okay, since a is greater than 3, this means compress. Correction means stretch. And since b equals 2, this means stretch as well. Correction, when b is bigger than 1, we need to compress. So there's a fair bit going on here already. I've got a h value of -3, which tells me I need to translate horizontally. Okay, and it's 3 units to the right. The horizontal translations are always the opposite to what you think. And a k value of 3 means we need to translate it up 3 units. So there's a fair bit going on there. The general rule is to dilate before translating. Okay, or stretch before you move. So let's have a go at doing that. I'll apply my two dilations. So I'm stretching it in the vertical direction like I've done before. There we go, stretching in the vertical direction. Okay, and then I'm horizontally dilating. So then get everything closer to the y-axis, so even closer than it is before. I'll do this in another color. So shift everything in closer to the y-axis. Okay, then I need to translate everything 3 units to the right. I'll do you in red. So from my green graph, everything goes 3 units right. And then finally, everything will go 3 units up. So shift everything just a nominal 3 units up. And that blue graph is what we'll end up with in the end. Something that looks something like this. Okay, we're not going to be able to draw these exactly. There's no markings on these axes, so it's just all indicative. Here are some questions to have a go at.